So this is the second practice exam for your final exam for Chem 210. Here we're going to take a look again at the structure of an alpha D-glucopyranose. In this case, you were given a Mills projection, and so your job was to be able to translate that into the other representations. Remember, Fisher projection is your open linear chain form, whereas the chair form and the Hayworth projection both show different facets of the carbohydrate. Remember, dashes in your Mills projection are down, whereas wedges are up. It's important to note that you can draw multiple chair forms. All you need to do is draw one. In this case, remember, your alpha means down. Right? In this case, it's axial and down for the chair form. And again, you can label that as the anomeric carbon. You can simplify the way you draw your mechanisms for the formation of the sugar. In this case, I just excluded all of the other hydroxyl groups that are present in the molecule because they're not relevant to the mechanism. Remember, my oxygen is my nucleophile and attacks my electrophile. That forms an ether and an O-, which will eventually get protonated. Remember, if that hydroxyl group is up, that's the beta form. If it's down, that's the alpha form. So this is a mechanism for forming a hemiacetal penultimate carbon. Oxygen, carbon-5, attacks from the top. It forms the alpha anomer. If the oxygen attacks from the bottom, it forms the beta anomer. Hemiacetal is one hydroxyl and one ether, whereas an acetal is a formation of two ethers. For example, the formation of an acetal could be a polymer of carbohydrates, such as a disaccharide or a polysaccharide. Which would have the higher boiling point, 1-butoxy-3,5-dimethylhexane or beta-D-glucopyranose. Why? Which would be more soluble in water? Why? So in this case, right, the 1-butoxy-3,5-dimethylhexane is predominantly an aliphatic carbon chain. There's really only one hydroxyl group. It's going to have minimal hydrogen bonding. Whereas if I compare that to the sugar, a glucopyranose, it's going to have a higher boiling point because it needs to break all of those hydrogen bonds. Also means that because of those hydrogen bonds, it's going to be more soluble. A lot of H bonding means higher boiling point and greater solubility. If we think about the formation and reaction of proteins in biochemistry, we know that in order to be able to draw a tripeptide, the first thing we need to do is actually draw our carbon chain. Keep in account that this is at pH 7. So here's my N terminus, here's my C terminus. So if I literally draw my carbon chain and then I add in my R groups, that's the easiest way to be able to draw peptides. So if we think about the table for the charge of the peptide above to the nearest integer or half integer, I think one of the easiest ways to do this is actually to create a table. So for each of the ionizable groups, so in this case the H3N plus, the carboxylic acid, the thiol, and then the C terminus, you're going to want to make sure that you identify the pKa's for each of these from the pKa table. And then you can go through and figure out the overall charge. Without doing any more calculations, specify a range for the possible PI, the peptide, and give your reasoning. So the PI for the peptide is when the net charge is 0, so it's likely around pH 3, somewhere between 0 and 7. If you actually wanted to do that calculation, you would average the closest pKa values on either side of the value. So 1.96 and 4.25. That gives you a PI of 3.1 approximately, which is exactly what our estimate was. Glycolysis is one of the central metabolic pathways. So here's an example of some of the reactions that are found within glycolysis. So here, this is an aldol cleavage where I'm taking my D-fructose 1,6-bisphosphate, and I'm literally cutting it in half to form the dihydroxyacetone phosphate and the glyceraldehyde 3-phosphate. Notice I need to convert that dihydroxyacetone phosphate into the other product, this D-glyceraldehyde phosphate. I do that through a tautomerization. So this is going from the ketone to the double bond to the aldehyde. So this is a tautomerization. And then the last step is an oxidation to take my glyceraldehyde 3-phosphate and convert that into glyceric acid. Notice I use G to represent everything else. There's no need to draw it out in its entirety. Understand the components of the mechanism for the formation of FADH2 and the likely products. So multiple mechanisms are involved in this cascade. The first mechanism is an acid-base reaction where the negative charge on the base deprotonates the hydrogen. The electrons from the bond between the hydrogen and the carbon are then used to form a carbon-carbon double bond, because carbon cannot exceed the octet rule. I have a hydride that leaves. The negative charge then on the hydrogen forces resonance. And the final action of a double bond is a nucleophile to take the last hydrogen. And notice this is the reason why FAD has two H's. How does the pH affect the behavior of water? Provide at least two examples of the molecular structure and the behavior of water. Make sure to reference any relevant pKa's. So water is a base. That's where water acts to take a proton. It's going to form H3O+, hydronium, which has a pKa of negative 1.7. Water that acts as an acid donates a proton. In this case, something's going to take that proton away, leaving us with a hydroxide base that has a huge pKa. So the pKa that we're most concerned about for water is a pKa of roughly 15.7. So why are carbonyl compounds considered electrophiles? What's the difference between electrophiles and nucleophiles? Provide an example of each. So electrophiles want electrons. Nucleophiles use electrons to form bonds. The formation of a shift base typically occurs between an amine, such as propylamine, and a carbonyl group, such as 2-butanone. Draw the mechanism below. So 2-butanone forms a resonance structure with the carbon as the electrophile. A lone pair on the nitrogen is the nucleophile. The formation of water by transfer of a hydrogen creates an exceptional leaving group. The formation of an amine is dependent on the removal of water, the leaving group. Otherwise, the reaction can easily shift equilibrium back to the starting materials. So notice here we have an application problem. So these are shift bases or common enzymatic intermediates where an amine, such as 4,4-diaminophenyl ether, reacts with O-vanillin. Molecules are drawn below. Draw the reaction of 4,4-diaminophenyl ether reacting with O-vanillin, primary component of the extract of vanilla bean. So here, my recommendation is you simplify your structures to make life a little bit easier for you. Anything that's not reacting, you can represent with an R or R2. And then you can actually show virtually the same amine attacking a carbonyl mechanism that you showed above. Again, where you're going to form water, water acts as the leaving group, then you have your transfer, and once water leaves, you can form your amine to give your final product. Functional groups are critical to reaction mechanisms in biochemistry. So if you're going to draw and label out functional groups, again, you can use symbols to help you categorize them. So alkanes, alkenes, alkynes, aromatic are all of your hydrocarbons, amines, thiols, alcohols, ethers, epoxides, as well as aldehydes, ketones, carboxylic acids, esters, amides, nitriles, isocyanate, anhydrides, azos, imines, and acyl chlorides are all great examples. Many functional groups have lone pairs. Arrange them according to the number of lone pairs. So this is an exercise that you're well familiar with by now. So those that have only one lone pair versus those that have two versus those that have three. I got overexcited and I shifted right in under the category. So these are the 4 lone pairs, 5 lone pairs are below, 6 lone pairs are over here. Closest, the relationship between structure and function is significant. Again, here you need to be able to identify R and S for tartaric acid. White crystalline organic acid that occurs naturally in many plants, most notably in grapes. It's salt, potassium bitartrate, commonly known as cream of tartar, develops naturally in the process of winemaking. So again, this is an exercise that we've done multiple times below. Just make sure that you are comfortable identifying both chiral centers, assigning R and S, and then also thinking about the role and relationship of meso compounds. Draw the mechanism for the activation of a fatty acid, such as decanoic acid with ATP. So in this case, your fatty acid is going to attack your phosphate, and then the 2 phosphates leave. This is going to create an intermediate that then reacts with CoAsh to generate AMP. So in this case, here's your fatty acid. That's going to react with CoAsh and ATP. That's going to give you your acyl-CoA. So this is the beginning of beta oxidation. Fatty acid attacks the phosphate closest to the sugar. The other 2 phosphates leave. The second nucleophilic attack results in the formation of AMP and acyl-CoA. This can then undergo catabolic processes where the beta carbon is cleaved, creating a 2-carbon segment, resulting in acyl-CoA, which is oxidized to carbon dioxide in the citric acid cycle. So how many cycles of beta oxidation are required to generate acetyl-CoA from decanoic acid? how many acetyl-CoA molecules are formed. So we know that acetyl-CoA have 2 carbons. That means I would form 5 acetyl-CoAs. If I wanted to figure out how many cycles, I would need to divide the total number of carbons by 2 and then subtract 1. That's going to give me the total number of cycles, so in this case 4. You now know all 4 primary metabolites and their role in metabolism. Label the nucleotides and draw the hydrogen bonds. Again, this is being able to distinguish between purines and pyrimidines. And then what are the 3 parts of a nucleotide? Where and what do they bond to? Label carbons and identified structures. So I have a phosphate, 5', 3', a sugar, and a base. These bind through the anomeric carbon. Remember, you can distinguish deoxy versus deoxy, which would be DNA, versus RNA. And then what type of structure is shown below. So this is deoxyribonucleic acid. How do you know? Because it's missing the 2' hydroxyl group. And that's it. Thanks so much. Have a great day.